welcome you in the lecture series of Basics of Communication Engineering. It is tutorial 9th based on lectures 25 to 28. Now, the question first is a signal is carrying data in which one data element is encoded as one signal element means R is equal to 1. If the bit rate is 100 kbps, what is the average value of the baud rate if the case factor is between 0 to 1? So you know the relation between signal rate and data rate, it is S is equal to C into R into 1 by R. This is the baud rate and this is case factor, this is data rate R, and this R is predefined factor. So here you have given R is equal to 1. If case factor C I consider 1 by 2, then S will be 1 by 2, and the data rate it is 100 kbps and R is 1. So the signal rate it is 50,000, or you can say signaling rate it is 50k baud. Now another question, an analog signal carries 4 bits per symbol element. If 1000 signals elements are sent per second, find the bit rate. Here we have given R is equal to 4, means 4 bits per symbol element. So R is 4 and S is 1000 signals are there. So what is the bit rate? If I consider C is 1, then S is R into 1 by R if C is equal to 1. So here R it will be S into R and it will be 1000 into 4. So it is 4000 bits per second or 4 kbps. Now next question. An analog signal has a bit rate of 8000 bits per second and a baud rate of 1000 baud. How many data elements are carried by each signal element? How many signal elements do we need? Here we have given the signal rate, it is 1000 baud, and data rate it is 8000 bits per second. So S is equal to R into 1 by R. So from here we can have, or R it will be capital S. So it is 8000 by 1000. It is 8 bits per baud. And since R is equal to log 2L. So from here L it will be equal to 2 is to the power R, and it is R it is given, we have calculated it is 8. So 2 is to the power 8. So the number of levels it is 256. So with 8 bits we can have 256 levels here. Now next question, we have an available bandwidth of 100 kilohertz which spans from 200 to 300 kilohertz. What are the carrier frequency and bit rate if we modulate our data using ASK with D is equal to 1? So the bandwidth is between 200 to 300, and the middle of the bandwidth is located is 250 250 kilohertz. This means that our carrier frequency it can be 250 kilohertz. So FC is 250 kilohertz. Now bandwidth, the bandwidth for ASK it is 1 plus D into S, and S is equal to R. If I consider this equation first, R into 1 by R. So here if since R is equal to 1 for ASK, so we have S is equal to R, and bandwidth it will be 2 into R because D is 1, and so it will be 2 into this is R. You have given R, it is bandwidth is 100 kilohertz. So from this you can calculate R, it will be 50 kbps. So bitrate it is 50 kbps. Now next question. We have an available bandwidth of 100 kHz which spans from 200 to 300 kHz. What should be the carrier frequency and bit rate if we modulate our data using FSK with d is equal to 1? The previous question was same, but we have used here the ASK modulation, but in this case we are using FSK modulation. So for this, the bandwidth, for the FSK, it is equal to 1 plus d into s plus 2 del f. Here the midpoint, as in previous case, it is bandwidth from 200 to 300. So midpoint 250. 2 del f, it should be 50 kilohertz. So here we can have del f, it is 50 kilohertz, and bandwidth it is 100 given. So bandwidth 100, it is equal to 1 plus d into s plus 2 del f. So here 2 del f is 50, so it is d is 1, 2 into s plus 50, it is 100, and from here to s it is 50. So from here we can have s, it will be 25 baud, and r, it will be 25 kbps. Now next question. Given the data stream 111001010, sketch the transmitted sequence of the pulses for each of the following line codes: unipolar NRZ, polar NRZ, unipolar RZ, and bipolar RZ, and Manchester code. So for this, this is the data or data stream 11100101000. So for this, the unipolar NRZ means, for this case, the 1 is represented by positive A, and the duration of this positive A will be equal to the duration of the pulse width. So it will be for the whole duration, so it is non-return to 0. And for 1 it is again plus A, and for 0 there will be no pulse, or the amplitude of the pulse will be 0 0 0, then 1, and again 0, and then 1 0 0. And now for polar RZ, now polar NRZ, polar non-return to 0. Polar means we are having the pulses on the both side of the time axis, and in unipolar we are having the pulse on one side of the time axis. But here for 1 we are having the pulse of amplitude plus A for 1, and the pulse of amplitude minus A for the 0. So for 1 it is plus A plus A plus A, and for 0 the pulse amplitude is minus A plus A minus A plus A, and then minus A. So here pulses are on both sides of the time axis, so that's why it is polar. And NRZ means in the duration of the bit, the pulses will not return to 0, so this is NRZ. Now next is unipolar RZ. RZ means return to 0. Pulses return to 0 in mid of the pulse duration. So here for the 1, the pulses will be at plus A amplitude, but at the mid of the pulse, the pulses will return to the amplitude 0, and it will remain during that again another half cycle. And for the again for the data 1, the pulses start from A, and it will be up to half of the duration of the bit, and in the next half duration it will return to 0. So that's why it is returned to 0 RZ. Unipolar means the pulses are on the one side of the time axis, and for 0 it is 0 0, and for 1 it is start from plus A and return to 0. It start from A and return to 0. Now another is bipolar RZ. Bipolar means it is on both sides and return to zero, means it will return to zero. Here you can see for one, this the pulses are represented as plus a, and in the mid of the pulse duration it will return to zero and remain during the next half. And here bipolar again, and for the data 1, here this time this pulse is represented by minus a and return to 0. So alternatively the pulses are represented by plus a and return to 0, and for another one it is represented minus a and return to 0, plus a return to 0. But for 0 there is no variation in the pulses, it is pulse of 0 amplitude. And again at this time this is plus a to 0, and this time minus a to 0, and for 0 there is no variation, and this is plus a to 0. And this is bipolar. Bipolar means for for one pulses there is no pulse transmission, and for another bit, for one bit there is no transmission or no pulse transmission, and for the another bit there is variation from plus to 0 and minus to 0. Now next is Manchester encoding. So here for the Manchester encoding we are having from high to low and low to high, means for the one the bit duration is divided into two halves. For one bit the pulses are remains at one level during during first half cycle, and it will go in the next level during the half cycle. So for the one the pulse duration is plus a, in the bit half bit duration it will return to minus a, and for the bit 0 for the first half it is at level minus a, and it goes to plus a during the next half cycle. So there is high to low for the 1 and low to high for 0 representation for the Manchester encoding. So this is one kind of Manchester coding, as you can see on your screen. Now another question. An FSK system transmit binary data at the rate of 2.510 to the power 6 bits per second. During the course of transmission, white Gaussian noise of zero mean and power spectral density 10 to the power minus 20 watts per hertz is added to the signal. In the absence of noise, the amplitude of the received sinusoidal wave for digit 1 or 0 is 1 millivolt. Determine the average probability of symbol error for coherent binary FSK system. So here the bit rate it is given, bit rate it is 2.5 into 10 is to the power 6 bits per second, and bit duration TB it is 1 by 2.5 times to the power 6, it will be 0.4 microsecond. And the signal energy per bit, so signal energy per bit it is EB, it will be a square TB by 2. So from here it will be 1 by 2 10 is to the power minus 6 whole square into 0.4 into 10 is to the power minus 6. So EB will be 2 into 10 is to the power minus 9 minus 19 joule. And for the coherent binary FSK, the average probability of error it is 1 by 2 ERFC EB by 2 N naught. And here you have given N naught by 2, it is 10 is to the power minus 20 power spectral density. So from here N naught it will be 2 into 10 is to the power minus 20. So the average probability of error it will be 1 by 2 ERFC 2 into 10 is to the power minus 19 and minus 19 and divided by 4 into 10 is to the power minus 20, and from here it will be 1 by 2 ERFC under root 5, and it will be equal to approximately 0.85 10 is to the power minus 3. Now next question. Binary data are transmitted over a microwave link at the rate of 10 is to the power 6 bits per second. The power spectral density of the noise at the receiver is 10 is to the power minus 10 watts per hertz. Find the average carrier power required to maintain the average probability of error. P is less than or equal to 10 is to the power minus 4 for the coherent binary PSK. Since for the coherent binary PSK, the probability of error, average probability of error, it is 1 by 2 ERFC under root EB by N naught. And here this is given if it is maintained 10 is to the power minus 4, it will be equal to 1 by 2 ERFC under root EB by N naught. And here RB is 10 is to the power 6 bits per second. So TB it will be 1 by 10 is to the power 6, you can say 10 is to the power minus 6 or 1 microsecond. So from here we can have ERFC, it will be ERFC under root EB by N naught. It will be equal to 2 into 10 is to the power minus 4. Or from here we can have EB by N naught under root, it will be ERFC inverse of complementary error function 2 into 10 is to the power minus 4, and it will be equal to, from the table of ERFC you can have, it is 2.63. So from here we have given under root EB by N naught, it is 2.63. So under root EB by N naught, it is 2.63. So from here EB by N naught, it will be 7, or EB it will be 7 into N naught, and you have given the power spectral density N naught by 2, it is 10 is to the power minus 10. So N naught it is equal to 2 into 10 is to the power minus 10. So EB bit energy 7 into 2 into 10 is to the power minus 10. So it will be EB it is equal to 7 into N naught, it is 14, 10 is to the power minus 10, or you can say it is 1.4 milliwatt. Now next question. The value of EB by N naught required to realize an average probability of symbol error PE, and that is 10 is to the power minus 4, using coherent binary PSK and coherent FSK systems. Now determine the separation in the value of EB by N naught for probability of error 10 is to the power minus 4 using binary coherent PSK and coherent binary FSK. So for the coherent PSK, the average probability of error, it is 1 by 2 ERFC under root EB by N naught, and probability of error it is given 2, 10 is to the power minus 4, and it is equal to ERFC under root EB by N naught. So this is the similar case as in the previous question, and we have calculated there EB by N naught, it was 7. So from here we can have, if I will take it in dB, 10 log 10 7, it will be equal to 8.5 dB. EB by N naught, it is 8.5 dB for this case binary PSK. And for the coherent binary FSK, the probability of error, it is 1 by 2 ERFC EB by 2 N naught. So here you can see it will be 2 into 10 is to the power minus 4, it will be ERFC EB by 2 N naught, or you can say here EB by 2 N naught, it is 7, and EB by N naught, it will be 14, or you can say it will be 10 log 10 14, it will be 11.5 dB. So here for the same datas, the probability of error for binary coherent PSK if I used, and for this the EB by N naught, it is 8.5 dB, and for coherent FSK it is 11.5 dB. So the separation in the values in EB by N naught, you can say the separation is 11.5 minus 8.5, and it will be equal to 3 dB separation between these. So the same probability of error uh, we can found using 8.5 dB SNR, but with FSK the same probability of error we can have using the SNR 11.5. So we can say that PSK is better than the FSK, and the SNR advantage is 3 dB advantage in SNR using PSK as compared to FSK. So this is the end of this tutorial, and in the next lecture we will discuss about telephony, telephone transmitter and receiver. Till then, thanks for listening this tutorial. Thank you.